Inside a hyperscale data center running continuous east-west training flows for a modern AI model, terabits of data move across the network every second. Scaling these massive clusters relies on a limiting factor that has nothing to do with the shortage of raw GPUs. The primary constraint is the processing friction created by network security and routing. For decades, data networks have operated under the assumption that security tools, like deep packet inspection and heuristic agents, need to understand the actual intent of the data. To secure a network under this semantic model, middle boxes must intercept the traffic, unencrypt the packets, parse the data, and evaluate against known logic signatures. This chart shows a server's total compute capacity. In heavy environments, the computational overhead required to constantly inspect data logic routinely consumes up to 30. Forcing packets through an inspection checkpoint injects non-deterministic latency into the data flow. In massive AI models, this latency and CPU burn drops your model flops utilization sharply. The hardware spends time waiting on data rather than computing the model. Adding more hardware fails to solve this because the semantic penalty scales proportionally with the size of the network. To reach true exascale AI performance, the network architecture must abandon the semantic inspection layer. Achieving maximum utilization requires shifting from discrete semantic logic to continuous deterministic topological physics. This approach stops asking the network, what is the intent of this data, and instead asks, what is the physical geometry of this data flow? The predictive tensor control plane, or PTCP, serves as the architectural foundation for this change. PTCP establishes payload-blind visibility. It ignores the actual content of the packets, continuously sampling the network's multidimensional telemetry instead. This vector space illustrates three tracked metrics: bandwidth, jitter, and queue depth. The control plane compresses these into a continuous structure known as a pattern-of-life tensor train. This compressed probability tensor operates within strict, mathematically bounded memory limits. Legacy endpoint detection agents frequently trigger CPU spikes when receiving a heavy influx of data. The tensor mathematics used here maintain the same minimal memory footprint, regardless of traffic volume. As data flows through the local hardware, the tensor updates itself to establish a precise geometric baseline of normal operational conditions. Any variation from this baseline is calculated as a mathematical discrepancy, removing the need to check a database of known threat signatures. This makes the network inherently resilient to zero-day vulnerabilities. Even a novel cyber attack cannot move through a system without leaving a measurable physical impact on the network's telemetry. PTCP transforms network telemetry into a deterministic mathematical security perimeter. Tracking individual telemetry vectors across millions of nodes becomes inefficient at the exascale level. To manage this complexity, the system shifts to a macro-level model called Tensor Network Quantum Gravity, or TNQG. TNQG treats the data center as a continuous, interconnected fabric of spacetime. When a zero-day exploit attempts data exfiltration, it creates a concentrated point of friction. The exploit inherently warps the network's geometric curvature, resulting in a measurable topological defect. Because the system identifies the anomaly purely through this physical geometric warp, it classifies the traffic as malicious with absolutely no decryption of the payload. Once the topological defect is verified mathematically, a quarantine instruction is issued directly to the hardware layer. Extended Berkeley packet filters and express data path hooks execute this block at the network interface card level. The malicious traffic is dropped from the connection before it can touch the host operating system or allocate any main memory. A legacy firewall must pull the entire packet payload into the host CPU's memory before it can decide whether to drop it. By shifting the evaluation to geometry and the enforcement to the interface card, the system burns 0 CPU cycles managing malicious traffic. The integration of TNQG and eBPF ensures that 100% of available compute remains isolated from network threats, and it remains dedicated to maximizing AI model flops utilization. This newly found architectural efficiency extends outward from centralized data centers into global telecommunication networks, reaching highly localized mobile edges. A 5G mobile edge compute node delivers ultra-low latency AI applications, like autonomous driving computations, without relying on distant servers. Backhauling edge traffic to a centralized cloud for deep packet inspection destroys the latency advantage the edge node was built to provide. Because tensor math is highly compressible, PTCP acts as a distributed autonomous sensor. Individual cell towers and edge nodes calculate their own topological security perimeters locally. On modern smartphones and modern IoT devices, legacy security agents maintain their perimeters by constantly polling the operating system, which drains the device battery. The PTCP omnibus cage uses local VPN loopbacks to draw a strict mathematical boundary around the device's outbound connections. Zero-click attacks like Pegasus operate within operating system sandboxes where legacy scanners are blind. However, the moment the exploit attempts to exfiltrate data, it violates the geometric baseline and is mathematically caged. The continuous tensor mathematics are compiled directly onto the device's neural processing unit to avoid taxing the primary processor. The system uses flow-level sampling, evaluating only the initial packets of a new connection to score a potential topological defect. Offloading payload-blind security to the NPU achieves zero-click immunity while delivering a significant increase in overall device battery life. We began with a 30% compute loss in data centers consumed by legacy security tools. Eradicating this bloat through topological physics allows infrastructure to reclaim those reserves of stranded processing power. This reclaimed efficiency leads to a plummeting cost for AI training and inference. This triggers the Jevons paradox. As the architectural efficiency of compute increases, the global rate of AI consumption and deployment rises exponentially. Making compute cheaper and faster lowers the barrier to entry, driving AI ubiquity across all enterprise sectors and telecommunication edges. As AI scales, the transition to geometric processing ensures the underlying infrastructure remains efficient, secure, and economically viable, from the core to the mobile edge.